So we're starting a new chapter here, and this chapter is really very different than the last few chapters. As a matter of fact, each chapter in this course is pretty different than the other ones. Like, think about the first chapter, right? That was all about techniques of integration. We did all sorts of techniques of integration. The second chapter was mainly applications of integration. And the third one actually has very little to do with integration at all. We're kind of going into a different area in a sense. It's called sequences and series. This is a little bit of more of an abstract topic, and some of you may be more familiar with this because you took pre-calculus. You may have seen some introductory level of sequences and series. And I must say in this chapter that the first section is about sequences. Everything else from that point forward is going to be about series. Now, as you know, a series is basically a sum of a sequence. And so you need to understand sequences really well to be able to continue on with the infinite series. One thing about this chapter that is really, really important to know is that the topics are dependent on each other. So for example, in the last chapter, you could have missed one day. So you could have missed center of mass, come back to fluid force. You would have no problem understanding fluid force, right? In this section, everything is building on top of each other. Like, if you miss sequences, there's no way you could understand the next class. If you miss the next class, there's no way you would be able to follow the third day. So it's very sequential. So I might give you some pop quizzes here, or maybe like short 5-point quizzes on most days, because I really want to make sure everybody does the homework before they come back to the next class, because the material is so dependent on the previous topics, and that will enhance your understanding of the material. Okay, let's start with the basics. Definition of a sequence. Basically, it's a function, but the domain consists of a set of positive integers. Okay, so like I said earlier, don't worry too much about writing everything down, because I will email the notes later on. Okay, so like a function, but domain is positive integers. Now, we know integers are whole numbers, so you can only have positive whole numbers as the values for n. Like, look at this example. N can be 1, 2, 3, 4. It cannot be negative values. It cannot be decimals, etc. So for example, a sequence a of n, or a sub n sometimes, is given by 1 plus 1 over n. The question is, first of all, to find the first few terms of the sequence. Let's first write the first 4 terms. And usually in this section, we're going to be interested in finding the limit of a sequence. First of all, write out the first 4 terms of the sequence. So let's start with a sub 1, or a of 1. So basically, we're just plugging in a 1 for n, right? So the first term would be 1 plus 1 over 1. Okay, what is the second term of this sequence? 1 plus 1 over 2. So just write out the first 4, because second question I'm going to ask is, what is the limit of the sequence? Can we predict based on the first few elements? So let's write the decimal values for some of these. So next one is 1.5. The next one is 1.33. The next one is 1.25. You can even graph these points. So when n was 1, a of 1 was 2. So that's this point right here. That's the first term of the sequence. When n is 1, the corresponding sequence element was 2. When n is 2, a of 2 was 1.5 over here. The next term was 1.33, so getting closer to 1, but still not there. The next one was 1.25, so even getting closer to 1. So let's say this is my line, y equals 1. Again, we've only graphed the first 4. Obviously, we could go and find a lot more, but do we have an idea what the limit of the sequence might be as n goes to infinity? The numbers are getting smaller and smaller, right? But the one in front of everything is staying a constant. The second part is what's getting smaller, right? Like 1/4. As n gets larger, that's going to be like 1/5, 1/6. That second part is getting smaller. Someone guessed, how about the limit of 1? Do you see that on the graph, that the points are getting closer and closer to 1, but they're never going to touch the actual function. It's like the asymptote, right? So that's really the limit. So in general, we can write it like this. We can say the limit of the sequence as n goes to infinity is equal to the limit of 1 plus 1 over n. And we know that 1 over n goes to 0 as n goes to infinity. Therefore, the answer is 1. So many times, just the first few examples, I'm doing specifically writing out the first elements and doing the graph. But in general, we're only going to look at the analytical equation and come up with a limit by using some of the properties of limits that we have learned so far. Okay, now I have a question for you. The question is, the difference between a function, which is 1 plus 1 over x, and a sequence, which is 1 plus 1 over n. So if the function is 1 plus 1 over x, the corresponding sequence is 1 plus 1 over n. What is the difference? Because we work with functions in all the math classes, right? We always deal with functions in terms of x. So is there a big difference between a sequence and a function? Well, this graph pretty much explains it. If you look at the bottom two graphs, the function consists of, let's see, who's going to let me write on top of this? Maybe not. The function f of x is a continuous function except at x equals to 0. It consists of these curves. Okay, this is the function f of x, which is 1 plus 1 over x. Now, what about the sequence 1 plus 1 over n? Now, can n be 0 or less than 0? N cannot be 0, but x cannot be 0 either. But remember, when you deal with a function f of x, we assume x can be, any possible real number. In this case, anything from negative infinity to 0 and then 0 to infinity. But when you deal with a sequence 1 plus 1 over n, what is n restricted to? Positive integers, right? So n can be 1, n can be 2, n can be 3. So when you graph the sequence, instead of getting those two curves, what you're going to get is just these discrete data points. This is the first one. This is the next one, the next one, etc. So what you're getting is you're actually getting discrete data points that lie on the original curve, but you're not getting the continuous function. So the thing is that the function and the sequence, they're so much similar in terms of their limits. Like look at this one. What is the limit of this function as x goes to infinity? Where does that red curve approach as x goes to infinity? 1, right? So the limit of the function is really the same exact thing as the limit of the sequence as n goes to infinity. So that's why all the properties of limits we've learned about functions, they also apply to sequences. Okay, so like if you have applied L'Hopital's rule in the past to a function, you can still use L'Hopital's rule to a sequence. All those shortcut rules you've learned in Calc 1, like degree of the top is smaller than degree of the bottom, then what is the limit? If the degree of the top is smaller than degree of the bottom, and you're taking a limit as x goes to infinity, what is the limit? 0, right? Because the bottom is growing at a faster rate than the top. All those shortcut rules that you've learned that apply to functions, they also apply to sequences because of the similar nature that they have, especially when x goes towards infinity. The corresponding function and the sequence will both have the same limit. So we can continue to use those properties. Okay, so next few examples also, we're going to list the first few elements, and from then on forward, we're going to look at some important or special limits, and we'll stop doing that. But again, to get a little bit better understanding about a sequence, let's list the first few elements of example number 1. A of n equals -1 to the n times 1 over n. Let's list perhaps the first 4 to 6 elements until we have a good understanding of what's happening, starting with a of 1. then list the first 4 terms and see if that's enough to give you an idea about where the limit is approaching. So if n is 1, do we get positive or negative? Negative, right? Negative 1 to the 1 would be negative, so you get negative 1 over 1, or negative 1. Okay? If n is 2, we get negative 1 squared is positive, so you have positive a half, right? If n is 3, what do we get? Negative 1/3. If it is 4, we get positive 1/4. So this one is fluctuating between negatives to positives and plus and minus. Let's see what the graph looks like. So let's say this is here negative 1. Over here it's positive 1. And say 1, 2, 3, 4. So the first one, the first term is at negative 1. The next one is at positive a half. Next one is at negative 1/3. Next one is at positive 1/4, etc. So even though it fluctuates, does there appear to be a pattern as n gets larger here? The terms are approaching to a unique number, perhaps? If this were continuous, I might join them. It's not continuous, but if it were continuous, you would say, okay, it's going like this in a sense, right? The oscillations are getting less and less. But here we just have the discrete data points, but these data points are, in a sense, on that curve. So where do the points appear to be approaching? 0, right? Even though they fluctuate in signs, plus and minus, ultimately they seem to be approaching to 0. And if you look at it this way, just an analytical way, take a limit as n goes to infinity of negative 1 to the n times 1 over n. Now think about it. First, cover up the part that says negative 1 to the n. We know that just the 1 over n part goes to 0, right? And 0 times anything, whether it's plus 1 or minus 1, that will also go towards 0. So without even having to graph it or look at the first few terms, we could have concluded that this is going to go to a limit of 0. How about the next one? What is the limit of b sub n, or b of n? By the way, sometimes some books write it like this, some books write a sequence like this, b sub n. It means the same thing. It's a sequence. This is the nth term of the sequence. So we want to take the limit as n goes to infinity of negative 1 to the n times n over n plus 1. The question is, what is this limit? Once again, we could write out the first few terms and from there try to get an idea. Or we could just think logically to see what's going to happen to this quantity as n goes to infinity. Does anybody see what the limit will be right away? Is this one going to be 0 as well? Let's take a look at the situation. Let's write the first few ones because it's a little bit different than the last one actually. So what is b of 1, the first term of the sequence? It's negative 1/2, right? N is 1, n plus 1 is 2. Okay, what is the second term of the sequence? Positive 2/3, right? What's the next term? Negative 3/4, right? The next one? Positive 4/5, etc. If there is a limit, it should be a unique value. You cannot have more than one value. That's completely contradictory to the definition of a limit. It should be a unique value to which the sequence approaches. And if we were to graph this one, so this is 1, this is -1, and then here are 1, 2, 3, 4, our whole number integer values. Okay, so at the first term, it was -1/2. Next one was 2/3, so 0.67. Say over here somewhere. Next one was -3/4, or -0.75. Getting away from 0, basically. Next one is 4/5. So getting larger in a sense towards, if I put some dotted lines here, it looks like this is trying to go to two places, right? It looks like these points are going to try to go there, right? And these points are trying to go here. But is it possible to have two values as n goes to infinity? If the limit exists, it should be a unique number, right? So in this case, does the limit appear to exist as n goes to infinity? If it exists, what is it? Remember, you cannot have two limits. If it's trying to go to more than one place, you just say the limit does not exist. So in this case, what appears to be happening here? Because it's trying to go to two different places, right? And how could you have guessed this without having to look at the graph and listening at the first few elements? Okay, first ignore the -1 to the n portion. Ignore that and just look at this portion, n over n plus 1. What is the limit of n over n plus 1 as n goes towards infinity? Degree of the top is equal to degree of the bottom. You could either use L'Hopital's rule, or if you remember those rules from Calc 1, they're really helpful in this chapter. If the degree of the top equals to the degree of the bottom, what was that limit? If the degrees are equal, ratio of the leading coefficients. Remember that? If you forgot that, it's no big deal because now you know L'Hopital. So differentiate the top, differentiate the bottom. You have 1 over 1 because you begin with infinity over infinity, so you can apply L'Hopital's, right? So n over n plus 1 then is all by itself is going to where? 1. But there is a -1 to the n up front. -1 to the n, that means it's going to sometimes be multiplied with -1, sometimes it will be multiplied with +1. So you see it's trying to go to two places then? Because this is trying to go to 1, and the first part is going to try to multiply by -1 sometimes, and sometimes by +1. So it's going to try to take it to this direction and that direction, so the limit doesn't exist. So how did the first one exist then? If this one doesn't exist, what was the difference there? That also had a -1 to the n, right? But what was the difference there, though? The 1 over n portion was going where? Where was 1 over n going as n goes to infinity? 0. 0 times -1 or 0 times +1 is still 0, right? So that limit existed. But when you have something different than 0, then that -1 or +1 that is trying to pull it into two different directions, and then the limit does not exist. Okay, any questions about this before we do some other examples, look at other techniques of limits? Okay, let me see what else I have here. Okay, now we're going to take a walk back to Calc 1 right now, just to review some important theorems, because these theorems are going to be used again in this chapter. Again, these are directly from your book. Please don't try to write these. Specifically, they're coming from chapter 2. It might be like section 2.3 or 2.4. And again, if you need to, I'm going to email these to you. So three important theorems. One is called the Squeeze Theorem. Some books call it the Sandwich Theorem. The other one is limit of a composite of functions, and the other one is properties of limits. We're just going to take a quick look to remember these things. First of all, what was the Squeeze Theorem? Basically, it's telling you that if you have three functions, f of x is squeezed between h of x and g of x. So f is between h and g. So that's kind of like f is sandwiched in a sense between h and g, right? And if you happen to know that the limit of g is L, if you happen to know the limit of h is L, then any guesses what the limit of f would be? That has to go to L as well. And the same, even though this limit was given for x goes to a constant, it still works when x goes towards infinity, and it still works for sequences as well. So if you can show that the function that you're trying to find the limit of is between two other functions, and if you happen to know the limit of both of those, then you can easily find the limit of them in the middle, because that will be the same as those two other limits. So you're trying to put it between two functions. That's the goal. Okay, let's look at the other theorem. This one has to do with compositions of functions. Say you have f of g of x. Like if you look at your group activity, there's a ton of examples like this. Say you have the square root of, let's say, n over n plus 1, something like this. Okay? And say we're going to take a limit of this as n goes to infinity. The inner function is n over n plus 1. The outer function is the square root function. This theorem is saying if you know how to find, first find the limit of the inner function, whatever that is, and then apply the function to that limit. So for example, just find the limit of n over n plus 1 as n goes to infinity. What is that limit? We just did that, right? What is the limit of n over n plus 1? Degree of the top equals to degree of the bottom. So what is that limit? Infinity over infinity, which is 1, right? Because it's not because it's infinity over infinity, though. It's not because if you apply L'Hopital's rule, derivative of the top is 1, derivative of the bottom is 1, so that means that, this limit is going to be 1. Now you have the square root of 1. So this theorem is telling you that first find the limit of the inner portion, which is the limit of g of x in a sense, and then apply the function. So the limit of inside is 1. So all you have to do is now find the square root of 1, basically, which is, what is the square root of 1? In other words, just tell me the final answer for this question. What is this limit? You have one function within another. When that's the case, you basically find the limit of the inner portion. In this case, the inner function is this. You find the limit of this, which is what? The limit of n over n plus 1 is 1. And now we're taking the square root of that. So what will the final answer be? The square root of 1. In other words, just 1. Anytime we write square root, that's the principal squared, always positive value. So in this case, the answer is going to be 1. You have 1 just like this, except instead of n over n plus 1, I think it's 2n over n plus 1 or something like that. So you need to remember this composite function theorem when you have one function within another. So start working from inside to outside. And then you have the properties of limits. This is just a quick refresher. Like if you have a constant multiple, you can take the constant outside. If you're adding functions, you can actually take the limit of one plus the limit of the other. But you have to be extra careful when you're dealing with infinity, because like for example, what is infinity plus infinity? What is infinity plus infinity? That's still infinity, right? But what about infinity minus infinity? 0. Is that really 0? No, it's not. But it's not a number. Infinity is not a number, right? We talked about indeterminate forms in this class, right? There were like 7 or 8 indeterminate forms. In the same section when we discussed L'Hopital's rule, we talked about indeterminate forms. So infinity minus infinity is indeterminate. That means you have to do something more to get rid of it. For example, what was infinity divided by infinity? This was indeterminate, right? Other indeterminate forms were 1 to the infinity. This was indeterminate. 0 over 0 was indeterminate, right? Infinity minus infinity is indeterminate. So anytime you're finding limits, if you end up with one of these quantities, indeterminate means try to get rid of it by trying to simplify the expression. If it happens to be infinity over infinity or infinity or 0 over 0, you can also use the L'Hopital's rule. Okay, now let's do some more examples, especially about what we just learned. For example, let's find the limit of sine n over n as n goes to infinity. Let's find the limit of sine n over n as n goes to infinity. I'll give you a hint. We're going to use the squeeze theorem here. So this theorem works really well when you deal with sine or cosine. Sine n over n. I'm going to try to squeeze between two other functions whose limits are easier to evaluate. For example, what is the largest sine function can ever be? Because we know the graph of the sine function, right? It looks something like this. The sine function, the largest it can ever be is 1, right? And what is the lowest the sine function can ever be? -1. So can you suggest a function that sine n over n will always be less than that? So I'm looking for what to write over here, something that is always greater than sine n over n. You know, sine n is always less than which number again? 1. And the bottom I can leave exactly as it is. By not changing that, you know, I still have a correct inequality here because sine n is less than or equal to 1. So sine n over n is less than or equal to 1 over n. Okay? How about on the other side? What could I write on the other side? Sine n is always greater than which number? -1. So here I can put -1 over n. So now I've squeezed the original question between two other functions. And these other functions are going to be easier to find the limits for, because what is the limit of this quantity as n goes to infinity? What is the limit of this as n goes to infinity? Think of it like 1 over infinity. It's negative, but think of it like negative 1 over 10, negative 1 over 100, negative 1 over 1,000. So where is it going towards? Is it really going towards negative infinity? Write out a few of those terms. Let's see what happens, okay? Like negative 1 over 10, that's negative 0.1, right? Negative 1 over 100, that's negative 0.01, right? Negative 1 over 1,000, that's like negative 0.001. So where do these numbers appear to be approaching? They seem to be approaching to 0, right? So the limit of the left-hand side seems to be 0. Okay, what is the limit of the right-hand side? In other words, what is the limit of 1 over n as n goes to infinity? So what is the limit of 1 over n as n goes to infinity? Where does that part go to? 0, right? The bottom keeps getting larger and larger, therefore the ratio goes towards 0. So now then, what can you say about the limit of the middle portion? Limit of sine n over n, that has to go to 0 as well, right? Now in the future, you know, you don't have to do something so extensive, you know, you can just look at this quantity, sine n over n. Okay? Just look at it and say, okay, I know the top is always bounded, right? Bounded between which two numbers? -1 and +1, right? Whereas the bottom keeps getting larger and larger and larger as n goes to infinity. So the ratio on the top is always bounded, a fixed number between -1 and 1. Over the bottom keeps getting larger, so the ratio keeps going towards 0. So the answer is 0 for the given limit. So the answer is 0. Okay. Now the second example is going to use that previous theorem about composition of functions. You have ln of n plus 1 over n, one function within another. So how could we find this limit? Limit as n goes to infinity of that quantity. So start from the inner portion, right, as we have just seen in the theorem. If you're trying to find limit of n over n plus 1 over n, rather. Okay, what is the limit of the inner portion, the n plus 1 over n portion? 1, right? Degree of the top equals the degree of the bottom. As n goes to infinity, that's going to go to 1. So that means this whole thing is going to go to ln, because on the outside there's the ln function, ln of 1. And what is ln of 1? 0. So the answer to that question is 0. Yes, because I looked at the inner portion. The inner portion was just n plus 1 over n. First, I found the limit of the inner portion. And that was 1 because degree of the top equals to degree of the bottom, and ratio of the leading coefficients was 1. What if I have something like this? Sine of the function. So say this is another example. Say we're finding limit as n goes to infinity of sine of 3n squared plus 5n plus 1 over 2n squared minus 1 times pi. Let's see what the answer to this limit question would be. Again, you have one function with another. First, find the limit of the inner function, right? What is the limit of this quantity? 3n squared plus 5n plus 1 divided by 2n squared minus 1. What is the limit of that quantity? Degree of the top is equal to the degree of the bottom. So take the ratio of the leading coefficients, 3/2, okay? And then there's a pi. So now you have 3/2 times pi, or 3 pi over 2. On the outside, still the sine function is sitting there, right? So what you should really find is then what? Sine of what? Sine of 3 pi over 2. So this is going to be the same as sine of 3 pi over 2. And what do we know about sine of 3 pi over 2? That's the bottom of the unit circle right here. What do we know about the sine value at that location? -1, right? The y-coordinate there, that would be -1. So the answer to the limit question then is -1. Okay. Now there are some limits that will come up very often in this section and the next few sections alike. And I call these some important limits. And here's a list of all of them. Yes. Let's take a look at those right now. And in the next few moments, I'm going to try to prove some of them. Now, on a test, I might ask you 2 types of questions. One type might be, I might say, okay, prove that limit as n goes to infinity, ln n over n is equal to 0. If that's the case, I want to see a lot of work, okay? But there might be other types of questions where you can just refer to these. On those questions, I would say you can use the shortcut rules. You can use the results from the important limits table. So in that case, you don't have to reinvent the wheel. We can refer to these and just use them to come up with a limit. So just read the question carefully. If the question states to prove something or to show that, then I'm really looking for the long method. You shouldn't then refer to the shortcut rules. If it didn't say that, then you can come back and refer to some of these important limits. Okay, so we're going to start by proving the first one. Limit of ln n over n is equal to 0. So we're going to prove some of these important limits, starting with number 1. And number 1 actually is going to be very straightforward. So proof of number 1. I'll come back to this page in a little bit. If you still want to write some of them, I'll come back to it. So first we're doing number 1. Limit as n goes to infinity of ln n over n. Again, one of the best tools that we have to deal with infinity is L'Hopital's rule. In this case, can we even apply L'Hopital's rule here? Yes, because we're starting with which form? We're starting with infinity over infinity, therefore we can use L'Hopital's rule, so let's use it. By L'Hopital's, this is equal to limit as n goes to infinity of, okay, differentiate the top separately and the bottom separately, right? What is the derivative of the top? 1 over n. What is the derivative of the bottom? In other words, derivative of n with respect to n. We're just differentiating the top and the bottom, right? So again, if the n's are giving you trouble, think about x. Like say this is ln x over x. The derivative of ln x is 1 over x, right? And the derivative of x by itself would be what? 1. Same thing with the n. So derivative of n would be 1. So here we have a limit of 1 over n now, which is no longer indeterminate. What is the limit of 1 over n as n goes to infinity? 0. How do we know it? Because the bottom keeps getting larger and larger, right? The top is fixed. The ratio keeps getting smaller and smaller. It goes towards 0. What we have just done is we have shown that the natural log function will always grow slower than the regular y equals n function because the ratio of ln n to n was 0. Now I want to show you an inequality. I'll keep referring back and forth to that inequality today. But what we've shown is basically just the first part of this inequality. Just the first part. Actually, we showed this, that ln n, when I put two less than signs next to each other, that means like ln n is much less than n, which means that if you take the ratio of the smaller one to the larger one, if you take anything from the left-hand side to anything on the right-hand side, so you're doing like ln n over n, or ln n over anything on the right-hand side here, that the ratio will be 0. Okay, so what did we just show? We've shown that ln n is much less than n because the ratio of ln n over n goes to 0. I'll keep coming back to this because we're going to show this inequality in many different ways. Just so you have a preview of the situation, basically ln n is one of the slowest growing functions there ever is. Okay, it grows very slow. And if you look at the graph of the ln function, it looks something like this. It grows very, very slowly. It's rising, but it's rising very slowly. As a matter of fact, this is why like sometimes scientists use the ln function when they're dealing with like huge quantities, like think of like chemistry experiments or sometimes physics experiments. If your numbers are like 10 to the 6, they deal instead with ln of the 10 to the 6 because that's going to be more like 6, something like close to 6, or like think about it, log of 10 to the 6. Log of 10 to the 6 is 6, right? So it makes large numbers small because it's growing very, very slowly. Even at a million, it's equal to like roughly 6 or something like that. Then something that grows a little bit faster than ln n is the squared function. Something grows a little bit faster than squared function is the regular, like y equals x, let's say. Something grows faster than is like x to a power, like x squared or x cubed, okay? Powers of x. Again, instead of n, I'm using x because we're more familiar with that. Something that grows faster than a polynomial because like x to the second, x to the third, x to the fifth, these are polynomials, okay? Something that grows faster is an exponential function, like think a being as 5 or 2 or 3. 3 to the x is always going to grow faster than any polynomial, okay? And when we say this is always going to grow faster, we mean after a certain point. The first few terms you plug in, this inequality may not be true, but after a point, and when you take limit as n goes to infinity, you don't care what happens first few terms, you care what happens as n goes towards infinity. The factorial function grows even faster than the exponential. And finally, one function that grows faster than anything else is n to the n. We're going to prove a lot of these things that I just stated for you. But if I was just to show you right now, say you know this inequality, okay? Then what would you say about the following? What is the limit of n factorial over n to the n? If you know this inequality is true, what could you say about this? 0. Basically, if you take anything from this inequality from the left-hand side and divide with something that is on the right-hand side of that, the ratio will always go to 0. What if I reverse it? Because what we're saying is we're saying n factorial grows slower than n to the n as n goes to infinity to the point where the limit of the ratio is 0. What if you reverse it? What do you think will be this limit? N to the n over n factorial. That'll go to infinity because the top is growing much faster than the bottom. That'll go towards infinity. So take a look. That's basically what's stated with number 7 up here, right? n to the n over n factorial is infinity. So the other way to state this is as follows. You can also state it like this. Limit as n goes to infinity of n factorial over n to the n, that is equal to 0. That's another way to state it. Okay, let's go back and prove another case. Okay, I'm going to prove number 2, because then number 3 will be a special case of that, basically. So let's go and prove number 2. Show that limit of nth root of n is equal to 1. Show that nth root of n is equal to 1. Okay. If you try to plug in the value, let's see what we have. Like, do we have infinity over infinity when we were starting? Do we have infinity minus infinity? What do we have here? What we have is infinity to the power of, nth root can be written as what? It's a power of what? 1 over n, right? So this is the same as infinity to which power? 1 over infinity. Now 1 over infinity goes to 0. So what we have here is something of the form infinity to the power of 0. Now this was one of the indeterminate forms we had seen before when we covered L'Hopital's rule. Infinity to 0 is indeterminate. You cannot always assume that it's going to be 1. You cannot always assume that it's going to be infinity. It could be something in between. For instance, I could have the following. I could have the nth root of e to the n. Okay. Technically, this is of the format infinity to the 0 power. This is of that format. But is the answer going to be 1? Let's think about it. What is the nth root of e to the n, by the way? That's e to the n over n, right? What is that? What is e to the n over n? E to the 1, right? E. So it looks like the limit of this is going to be e, the limit of this. So don't assume just because you have infinity to the 0, it's automatically going to be 1. Don't assume that, because it doesn't have to be that way. Like I've shown you in this very example, it's not always like that. So when you have infinity to 0, you have indeterminate form. That means you have to apply some technique to get rid of that. Now, what do we learn in the chapter of L'Hopital's rule? If you have a variable base and a variable power, what was a good way to find a limit? I'll remind you something. Say, let y be equal to nth root of n. In other words, n to the 1 over n. If I need to find the limit of this, what was a good idea to do first? If you have a variable base and a variable power, what was a good idea? Anybody? To find the limits? Excellent. Kevin had the right idea. Apply natural log to both sides. So if you have a variable base and a variable power, you're trying to prove a limit. First, apply ln to both sides. So here we have ln y is equal to ln of n to the 1 over n. Then bring the power down. ln y equals 1 over n times ln of n. And now take the limit of both sides as n goes towards infinity. So take the limit of this side and take the limit of this side. Okay. Now the right-hand side should be pretty easy because we just did that. That was number 1, was it not? The limit of ln n over n as n goes to infinity. What was that limit? We know ln n grows slower than n, right? That ratio then goes to where? If you forgot, check back with number 1, right? So the ratio goes towards, let me rewrite it. This is the same as limit as n goes to infinity of ln n over n. So what was that limit? William, would you agree that ln n over n is going to be 0? So do we agree that ln over n over n is going to go to 0? Because degree of it's not really a degree, but you could apply L'Hopital's rule once again. We just did this, right? So that goes to 0. So what we're saying is we're saying limit of ln y is going to be 0. But that is not what the question was asking, right? We want to find the limit of the original expression, which was y. So what will be the limit of y? So basically think of it as an equality. If ln y is equal to 0, what can you tell me about y? If ln y is equal to 0, what is y then? Chris is right. It's going to be 1, right? How do we know it? It's basically e to the 0, right? Anytime you try to get rid of an ln, you exponentiate both sides, right? And it's going to be e to the 0 or 1. So the answer to the original question is going to be 1. The limit of y would be e to the 0 or 1. So that's what we were trying to prove, and that's what we have just proven. That basically the nth root of n, the limit of that is going to be equal to 1. Okay. All right, let's go back to our list, see if there's something else. Okay, basically the next one is going to be very, very similar. As a matter of fact, the next one is not even indeterminate form. Take a look at number 3, a constant, a positive constant to the power of 1 over n. That's not even indeterminate, right? Where does that power 1 over n go towards as n goes towards infinity? Where does 1 over n go towards? As n goes towards infinity, where does 1 over n go towards? It goes to 0. Now, c is a constant. It's not like our last example where c was like it was an n on the base and n on the power. No, c is just a constant. So now you have c to the power of 0. Guess where that goes towards? It goes towards 1. So that's really, you don't even need a fancy proof for that one. Now, number 4 is also going to be pretty straightforward to explain, but we're going to spend some time on number 5, okay? Number 4, it says as long as r is a number whose absolute value is less than 1, and if you keep basically raising it to a very high power, it goes towards 0. Just try this example. Say that r is equal to a half, okay? So if you have like a half to a very large power, say 100th power, or even the 10th power, where does that number approach? As the power gets larger and larger. So basically what you're doing, a half times a half times a half times a half. So what is happening to the number basically? It's approaching towards 0, right? So if you take a number that is less than 1 and keep multiplying it by itself, larger and larger number of times, the ratio or the product is going to approach towards 0. But what would happen if the base was a little bit larger than 1? So it wasn't less than 1. Say it was like 1.01. Say you had something like 1.01 to the power of n. Would that also approach towards 0? It's just a little bit more than 1, right? Do you think this is going to still go to 0 or? That's not what number 4 is saying, right? Number 4 is saying the base has to be less than 1. That's the only case under which you can say the answer will be 0. This base is not less than 1, so this is not going to go towards 0. As a matter of fact, anytime you have a number larger than 1 and you keep raising it to a very high power, it may go towards infinity. Okay? And finally, this number 5 is really, really important. You know, it looks so abstract. We keep taking these limits, but believe it or not, this number 5 here is the theory behind the exponential growth formula. Remember that formula A equals PERT? You know, the way money grows in a bank when you keep investing it over and over and the compoundings are continuous. Remember that formula A equals P times e to the RT? Again, this formula, basically, this number 5, is the basis in how that formula is proved, because it's showing you as you increase the number of compoundings n, you end up with this exponential value up here, the e to the a that we see here. So again, that is the basis of the proof of that famous formula that accumulated value equals P times e to the RT. This is the exponential growth formula. Whether you're investing money in a bank, whether you're looking at how bacteria grows in a culture, you usually end up with an exponential growth pattern. Okay, let's prove number 5. Limit of 1 plus a over n to the n is e to the a. So we're going to prove number 5. Limit as n goes to infinity of 1 plus a over n to the n is equal to e to the a. A very surprising result. On the left-hand side, there was no e whatsoever. There was just an n, there was an a. All of a sudden, in the answer, this exponential natural base e pops up. You know, a very unexpected result, a very important result. Like I mentioned, it's used in a lot of those exponential growth formulas. Okay, how could one go about proving something like this? Don't look at the right-hand side right now. Only look at the left-hand side. We're trying to find the limit of that quantity. If you have no clue what the answer will be, let's first plug in the values. Okay, see what's going on. As n goes to infinity, where does that go to? 1 plus, okay, a over infinity, that goes towards 0, right? And on the top, you have something that goes to infinity. So what you have is you have something that goes to 1 on the bottom and something that goes to infinity on the top. Okay? And unfortunately, there is no shortcut for that. 1 to the infinity is still indeterminate. You know, I get this question asked a lot. They say, okay, you know, why is that not equal to 1? It's a very good question. You know, why is 1 to the infinity not equal to 1? Because the catch is, it's not really 1 to the infinity. The catch is, the bottom is approaching to 1, and the top is approaching to infinity. If you really have 1 to the power of n, as n goes to infinity, this is obviously 1 to the infinity, right? There's no approaching going on here. This is clear-cut 1 to the infinity. And what is the answer going to be there? Clear-cut answer. It's 1 times 1 times 1 times 1 times 1, infinitely many of products. That's a 1, right? There is nothing ambiguous about that. But what's ambiguous is when the bottom is approaching to 1. Because you see, you don't have just a 1 down there, do you? You have 1 plus a over n. So that's approaching to 1. And the top is approaching to infinity. That's when we have the ambiguous case. That's where the answer could be anything. You cannot assume it's going to be 1. Like in this case, it's not 1, it's e to the a, something out of the blue, right? So you just have to take it case by case. 1 to the infinity is indeterminate form, as long as the base is going to 1 and the top is going towards infinity. Okay. How would one prove something like this? Let me give you a hint. You have a variable on the base, which is 1 over n, and a variable on the power, which is n. So any thoughts about how I could prove this equality? Let y be equal to 1 plus a over n to the n. I see the variable here is n. A is just a constant. Assume a is a constant. Is basically any real number. So the variable is n here. So there's a base has a variable, and the power has a variable. So let's take Kevin's suggestion from the last problem. What was that suggestion when you have a variable base and a variable power? Let me see if anybody else remembers it. Anybody was listening to his suggestion? Exactly, Garrett. Apply ln to both sides. Anytime you find yourself in this situation, a variable base and a variable power, go ahead and apply ln to both sides. So ln y equals, and as I'm applying, I'm going to bring the power down. So n times ln of 1 plus a over n. Okay. Now what do we have? As n goes to infinity, we're going to have infinity times ln of 1, which is 0, still in the determinate form. But anytime you have infinity times 0, you can rewrite it as 0 over 0 or infinity over infinity as follows. ln of 1 plus a over n divided by 1 over n. Okay, what have I done here? I just applied a little trick. The trick is, think backwards. If I'm dividing by 1 over n, is that the same thing as multiplying by n? Now, what was the advantage of doing this? Let's take a look for a moment, okay? As n goes to infinity, where does the top approach? As n goes to infinity, the top approaches towards 0, because ln 1 is 0, and the bottom approaches towards 0. Why is it advantageous to have 0 over 0? Which property, which rule could I apply rather? if I have 0 over 0 or infinity over infinity. Our good old friend L'Hopital's rule, right? So that's exactly what we're going to do. We're going to apply L'Hopital's rule. And if you're thinking this is getting really complicated, is this whole chapter going to be this complicated? No. You remember the first section when we introduced derivatives in Calc 1? You know, we were doing limit as h goes to 0. We were doing everything the long way. But then after we got those rules, we went back and we did some shortcut rules. And on the test, you know, I only asked you like 1 or 2 questions with the long method. Like 80% of the questions said use the shortcut rules. So once we can prove some of these table values for important limits, we're going to go back and just apply the results. We don't have to prove it every time unless if the question asks you to do so. So this is probably the last proof I'm giving you, and then we're going to do some shortcut rules after this, okay? So let's simplify this. We have 0 over 0. We're going to apply L'Hopital's. L'Hopital's rule says, okay, take the limit of the top, first rather differentiate the top and the bottom separately. Let's do the bottom because it's so much easier. What is the derivative of 1 over n? What is the derivative of 1 over n? Think of 1 over x. Garrett, do you have any questions? Do you have any suggestions? Okay, 1 over n. How about this? Would you agree with this? Would everyone else agree? The derivative of 1 over n is negative 1 over n squared, right? Okay. How about the top? The top is going to take more work. We're trying to find the derivative of ln of u. What was the derivative of ln of u? 1 over u times u prime. Okay. 1 over u will be 1 over the whole quantity. Okay. Now I want to know what is u prime. The derivative of 1 is 0. What is the derivative of a over n? Think of it as a times 1 over n. What is the derivative of a times 1 over n? Think of the derivative of 1 over n first of all. William, would you agree with me that the derivative of 1 over n is negative 1 over n squared? Okay, but there's an extra a up there. So what am I going to do? Multiply. So it's going to be negative a over n squared. That is the derivative of, that's my u prime. So this part is the 1 over u part. This is the 1 over u. And this is the u prime. Okay, that's my magical pen there. Okay, so a lot of simplifications that we can do at this point. The negative 1 over n squared from the bottom cancel with negative 1 over n squared from the top. So I'm left with the following. The negatives cancel completely, so I have 1 over 1 plus a over n. Okay, who can tell me what the limit of this quantity is as n goes towards infinity? Oh, sorry, I still need an a up there. Thank you. Okay, so where does this quantity go towards as n goes towards infinity? First, look at this part. Where does a over n go? Think of a as 5. Okay, what is 5 over n approach as n goes towards infinity? Think of it like 5 over infinity. Where does it go? 5 over infinity. Like, it goes towards 0, right? Okay, so now you have 1 plus 0, which is what? It was 1 last time I checked, right? So now you have a over 1, which is a. Okay, are we done? Always a good question to ask, right? Are we done? Did we answer what they were asking? We found the limit of ln y. So ln y is equal to a. Ln y equals to a. So what can you tell me about y then? E to the a. So the original question, limit of y will be, and remember what y we called y was the original question basically. That's going to be e to the a. The limit of the original question equals e to the a. Wasn't that what we were trying to prove up there? Take a look. That's exactly what we're trying to prove, right? The limit of 1 plus a over n to the n equals e to the a. Now remember this, because there's going to be a lot of problems that will say, what is the limit of such and such? You don't have to do all these steps if you just remember the answer. But on the test, I'm likely to ask you another question saying, let's say, prove that or show that this limit is equal to the right-hand side. So if that is the case, then you would show all the works, okay? All right, now let's do some examples. Okay, these are going to be much simpler problems because we're going to use shortcut rules. Okay? Think of this one, 1 plus 1 over n to the n. Look back to that problem we just did. What would be this limit? Because what is the a here? The rule said limit as n goes to infinity of 1 plus a over n to the n goes to where? E to the a, right? Here you have 1 plus 1 over n to the n. So in one simple step, we're going to put the answer. What is the answer once again? E to the power of, what is our a here? Our a is 1, so the answer will be e to the 1 or e. Again, this is a very famous limit. Some books actually define the number e with this limit. Limit of 1 plus 1 over n to the n, that's the same as e. Again, a very unusual result. There's nothing to do with e in the problem, but somehow e comes in the solution. How about this one? 1 minus 2 over n to the n. What is this limit? Let me give you a minute to think about. The answer will be e to the something, right? Because this is of the form 1 plus a over n to the n. What is our a in this case? Is it 2? Negative 2, right? Because the format is 1 plus. So you can write it as 1 plus negative 2 over n to the n. So the answer is going to be e to the negative 2. Again, if you just remember that rule, you can apply it for these examples using the shortcut methods. Okay, how about something like this? The limit of 1 over 4 to the n as n goes towards infinity. The limit of 1 over 4 to the n. Again, you can think back to one of the shortcut rules. It's going to be 0 because r, the base, is less than 1. The answer is 0. How about this one? This one you didn't really need today's lesson to do this one. You already knew how to do this one, but let's do it anyway. Anytime you have ratio of polynomials, you can use the rules from Calc 1, or you can use L'Hopital's rule. Does anybody remember what the answer will be here?
0, because the greater degree.
The degree of the bottom is higher than the top. Or apply L'Hopital's rule a few times, you're going to end up with 0 very quickly. So the answer is 0 because the degree of the top is smaller than the degree of the bottom. Or you use L'Hopital's rule. This next example, I want to do it later on. I think I'm going to... E and F, don't worry about right now. We're going to come back to those next time. Right now, let's do G. The limit of ln of n squared divided by n. We've just proven something about ln n over n. But ln n squared might be a little bit different. Who knows? So let's use L'Hopital's rule to try to prove this. We're beginning with infinity over infinity, so you can use L'Hopital's rule here. let's simplify the top first. That's the same as 2 ln n over n. Now does this look familiar? Ln n over n, we already know where that goes to, right? Where does it go to? That's rule number 1, right? That goes to 0, or apply L'Hopital's. And now you can have 2 times 0, so that goes to 0 as well. So once again, the ln function is growing smaller than the regular n function. And how about this one? Call this one h. Find the limit as n goes to infinity of e to the n over n cubed. Some of you can look at this problem and know the answer right away. But still, go ahead and show me some work. Okay? The top is exponential, the bottom is polynomial. Which one do you think grows faster? Exponential with a base greater than 1, that grows faster, right? So where do you think intuitively this might go? If the top grows faster, the ratio might go towards? If the top grows faster, this is like a million, this is a 10. This is 10 billion, this is like 1,000. You know, it's growing much faster on the top. So the ratio might go where? Towards infinity. So that's a guess because of what we saw. Now let's prove it with L'Hopital's rule. If you differentiate it 1 times, what would you get? Still infinity over infinity, right? If you do it again, take a limit, differentiate it again, you get e to the n over 6n. Still infinity over infinity. Do it 1 more time. E to the n over 6. Now where is it going? The top keeps getting larger and larger. The bottom is fixed. So where do you think this is going to go? It's going to go towards infinity. So our original guess was correct in that case. Okay, I didn't today have a chance to go back and prove the last few identities here, but I just want to make sure you guys look at these once again. These are very important. You're going to see a few examples about it in the group activity on homework. So if you see it, even the exponential function doesn't go as fast as the factorial. So look at number 6. If you take a ratio of exponential function over the factorial, that ratio will still go towards 0. So the last few properties at the moment, just feel free to refer to them. And later on, we're going to still talk a little bit about the proof of at least number 7 and possibly number 6 also. Okay. Let's see. Okay, I think I'm going to stop here. The second part of this, I'm going to probably continue next class. Okay, I'll be right with you.